Today what we're going to do is kind of wrap up the stuff we need to understand the correlations part of this and then talk about turbulent flow. So the first thing in this, this particular slide, I kind of struggled on how to approach this. But the main outcome I want from this is for you just to understand why is it that when we're talking about correlations, we represent correlations in a certain way. And I will also apologize, this little table, I didn't include it until today. So if you printed out the notes, you didn't have this. But what I want to do is to start, if you remember your fluids class or maybe some other physics class where you talked about continuity, if you went through and derived the equations for continuity, so like looking at a differential control volume, and then you apply the conservation of mass, you get this continuity equation. You can do the same thing for momentum, or you can go through and derive a conservation of momentum. You can derive a conservation of energy. So we're not going to do that because it's really tedious. I do that in 564. So that's a good selling point. You want more tedious things. But you can go through and you can apply the conservation to differential control volumes in X and Y, right? It's a two-dimensional thing. And you get these equations out. Well, you actually don't quite get these equations out. You get the dimensional form. So what you can do with the dimensional form is go back and non-dimensionalize these things. So here what you see is these equations, this continuity equation here, is in terms of, let's do it this way, is in terms of this like U tilde and V tilde and X tilde and Y tilde. So these are just non-dimensionalized forms of these dimensional quantities. So you'd say, for example, non-dimensional U, right? So U tilde would be, let's just call that U over U infinity. Right? So I have some like normalizing quantity. In the case of X, that might be my current X position over the full length of the plate L, right? So X over L. Y might be Y over L, and so on. So you go through and non-dimensionalize these. And why do we do that? Well, one, it kind of makes them useful in any situation. But two, it produces these little groups of terms, right? So out in front of in the X momentum term, in front of the diffusion part of the equation, you have 1 over Reynolds number. Right? So the Reynolds number, by non-dimensionalizing the X momentum, the Reynolds number actually comes out of that process. Right? So you remember doing like Buckingham pi theory and coming up with these dimensionless parameters. You can get to the same result by non-dimensionalizing these types of equations. Okay, so you get the Reynolds number out of the X momentum. Out of the energy equation, you get Reynolds, or 1 over Reynolds times Prandtl, and these groups over here. So I want to just briefly talk about what these are, but the main thing that you should understand here is that by non-dimensionalizing, excuse me, by non-dimensionalizing, we end up having these terms or parameters that come out that are directly related to the conservation equations to begin with. All right, so let me just reset my view here, hopefully. Okay, so what we end up with is we want these correlations. So let's say we want to represent the friction coefficient. Right, let's say I want a correlation for friction coefficient, C sub F. Well, if I look at the conservation equations, I can see what it is functionally dependent on. Friction coefficient is going to be related to X momentum. So anything that's involved with X momentum has to be accounted for in my correlation for coefficient of friction. Right? So you kind of want to stick with me through this slide. It's a little bit scattered, but so we'd say I need a function that involves this stuff in continuity, which is X tilde, which is Reynolds number in terms of L, and which is this dp tilde dx tilde. Right, so I would need some function that involves that stuff in order to capture the relationships there. So ultimately, when we look for a correlation, we're looking for correlations that involve that stuff. All right. If we're looking for a friction coefficient that's average over some distance, now instead of needing X tilde, Reynolds, and dp dx, if it's average, we just sort of integrate out that X. So now we'd only be looking for some function in terms of Reynolds number and dp tilde dx tilde. Okay? So again, it's trying to kind of ground you in what we're looking for in correlations. For energy, if we look at the energy equation, let's say I want to come up with some correlation for Nusselt number. So Nusselt number is going to have some functional dependence on everything in the energy equation. So I've sort of zoomed too far out to see, but that is x tilde, that is Reynolds in terms of L, that is this dp tilde dx tilde, and it is Prandtl number, and it is this group EC. EC is the Eckert number. So again, it's not going to be super important that you understand what that is. I'll tell you what it is in a second. But if I want to account for everything, I have to account for all of that. So my correlation is going to have to include all those things. If I do the averaged, it's going to be the same thing, but without the x tilde. So Reynolds, L, dp, dx, Prandtl, Eckert. All right. So the Eckert number, I'll just kind of tell you what this stuff is. Eckert number, E-C-K-E-R-T, it's the person, Eckert. The Eckert number is essentially a viscous dissipation term. So EC is going to be U infinity squared over C, the specific heat, times T infinity minus TS. All right, so this comes out of that energy equation. So why do we care? Well, we want as simple a correlations as possible. So if I can somehow figure out that, okay, this Eckert number, or at least how it relates to the rest of the equation, if that's not important, then I can just neglect it from the correlations. So when is it not important? If EC over RE is small, then we can neglect the contributions of the viscous dissipation. Okay, so maybe stop and think about what I'm saying. Again, I realize this is a little bit of an esoteric slide, but what I'm saying here is we want to reduce down our correlations as simple as possible. So Eckert number somehow relates to viscous dissipation. What is viscous dissipation? It is heat generation in the fluid related to the motion of the fluid, right? You have fluid shearing over itself. That friction can generate heat. In most situations, that's probably not important, right? The shearing heat generation is probably not important, but in some it might be. So if Eckert over Reynolds is small, then we can neglect viscous dissipation, right? And that's great. Then it simplifies our correlations. We don't have to account for it, right? That's all I'm trying to say there. There's another number that you should know, and that is the Peclet number, P-E-C-L-E-T. Peclet number, and that is normally P-E is equal to Reynolds times the Prandtl number. Let's see, so if conduction in the flow direction is important compared to advection, then the Peclet number is small. Right? So what I'm saying there is, if you compute this number and it's really small, then you can basically neglect conduction in the direction of flow. Right? Yeah.
When you say it's small, like how small? What magnitude?
Well, okay, so normally Reynolds number is going to be a big number, right? Prandtl's going to be somewhere around like 1. So if you have, let's say, Peclet number that's like less than 1, right? That's saying, if you think about it, that's a really, really slow flow, right? Because Reynolds number to be that small would have to be really, really slow. So if it's a really, really slow flow, then that means that there's a lot of time for heat to transfer in the x direction. So that's not really an answer to your question, but it's like, to give you a sense of the magnitude, you'd have to have a really, like, say smaller than 1 for it to start to kind of make sense that conduction in the flow direction is important. When it comes down to like what's the cutoff, I don't have a good answer for you off the top of my head, but it's it's going to be a small number. Yeah. Good question. Yeah?
What do you neglect again if the Peclet number is small?
So if Peclet is small, let me make sure I get this right. So if Peclet is small, then you can't neglect axial conduction. I think I might have said that. Right? So think of it again like you have a really, really slow flow where you have all kinds of time for conduction to actually occur in the direction that flow is moving. So if you have that situation, Peclet is really small, then you can't neglect axial conduction. And it changes the correlation, right? It changes what you have to consider. So maybe let me write that down. So neglect axial conduction, right? That's in the flow direction, in flow direction when Peclet is large. I'm going to say large and put it in quotes because I don't have a good rule of thumb number for you to use. But in almost every single situation, it's a large, it's negligible. Okay, so let's see what else to say here. All right, so again, the goal of correlations is to reduce down to the base number of variables, these parameters, the most basic number of variables or parameters that we can then express the geometry or whatever we care about, or express a correlation or drag coefficient or whatever in terms of that fewest number of things possible. So the fewer things we have to express it in terms of, the fewer like experimental data points we have to collect or simulations we have to run or whatever the case might be. So for our situation, in almost all cases, I'll just point out that we can neglect, for most cases, we can neglect dp dx. That is, the pressure gradient in the x direction is usually small, and or it's like given to you as part of the problem. So we can usually neglect. We can usually neglect the Eckert number as well. Reynolds number, Prandtl number, we're almost always including those. Okay, so it took more time on that than I wanted to, but let's now look at an example of this. So let me flip the view so you can actually see it. So let's say we have a sphere. And this sphere, I want to basically represent the, sorry, this should be C sub D. C sub D, that's the drag, C bar sub D equals C bar sub D, REL. Sorry about that. So what we want is to say, I have some drag coefficient, right? That drag coefficient is a function of something. For a sphere, it turns out I can boil everything down to the Reynolds number. So if I can somehow compute the Reynolds number for whatever the size sphere, whatever the properties of air, whatever else is happening, as long as I can compute the Reynolds number, I can represent the drag coefficient of the sphere, which is a really actually powerful thing to be able to do. Because it's like this universal thing, you can apply it to any situation. You don't have to have like a correlation for every single sphere diameter and fluid and all that kind of stuff. Right, so this plot on the left is showing you the drag coefficient for this situation. By the way, remember, I didn't put it up before, the drag coefficient is related to the drag force in this way. So it's 2 times the drag force over rho u infinity squared times the projected area AP. Okay, so AP would be pi times diameter squared over 4. It's the projected area of the sphere in the flow direction. Okay, so then the Nusselt number, like same type of thing. We can basically represent the heat transfer of flow over a cylinder in this case if I am able to compute the Reynolds number and the Prandtl number. So these two non-dimensional parameters, compute those, and then you have this family of curves, and I could just come over here and say, okay, my Reynolds number is this, and my Prandtl number is this, and so I know this is going to be my Nusselt number. right? And it's a really quick and powerful way to handle a large number of situations.